Did that succeed?
Yes, you can
Very
see a
good.
screen.
All right. Well, hello everyone. This presentation is a brief overview of Chapter 3 of the Building Performance Simulation for Design book. These sessions are being presented by each chapter author, and then all of them will be available for subsequent viewing. So I'm going to go through the first portion of the chapter and then hand it over to Drew. That's it's pretty obvious, but that you need the data ideally right at the site. Now the perfect solution would be to set up a weather station at the site and wait 10 years and then you'd be ready to go. That's obviously not practical. So the field relies on data that is observed generally for purposes other than building modeling or engineering purposes. And the most prominent one is aviation, but also weather forecasting, agricultural uses, etc. And our application is perhaps being recognized more, but it's pretty much we've had to deal with whatever data is available and adapt to it. And the match with available data is improving some because the cost of observation is going down. Automated weather stations, all sorts of things are readily available. There's more and more data around, but it's still, for the most part, a little bit making do with other people's data. So the general requirements for building simulation weather data are you need the right data for the problem. This is a key thing that this relates back to what Professor Agenbro presented in the last talk, which is that you got to understand your problem to know what you need to solve it. For instance, if you're trying to study daylighting, you need illuminance data. There has to be something, you need the conditions, the available light in the environment. Similarly, for natural ventilation, you need wind data. So some weather files are better than others, providing different classes of data, and it's important to understand what the sources of the data and what their reliability is, and that's one of our purposes here, to go over that a bit. So traditional data for simulation is an hour, 1 hour time step, and that's short and not super short. And that time step came about sort of naturally because of the that's a very natural interval to simulate building operations. But as we get more and more detailed simulation methods, and we're not limited by computer power as much as we were, shorter steps may be needed. And I'll talk about that a little bit later on. So as a result of this, a very common form of weather data is a file that contains 8,760 hourly records. Each record for an hour. Full year has 8,760 or 8,784 hours in it if it's a leap year. And so, as I said, that the 1 hour is the typical time step, and it's also the typical observation interval of detailed weather data for human sites where there's actually a weather observer. As I said, with automated systems now, you can observe every 10 minutes or any interval you want, because it's no longer a personnel issue. Another very important thing about weather data is that it's got to be what we call clean, and that means that there's no missing data, there's no negative solar gain, etc. It's got to be suitable for the software, and that's because bad data breaks software, and this can happen. You can have situations where you have, for instance, solar gain, or solar radiation, but the sun is down, according to the geometric calculations. And depending on how the application software is coded, that can actually break the software and cause it to crash. Whereas weather data observed for other purposes, where human beings looking at it, they say, oh, that's stupid, I'll ignore it. So it's very important to have good clean data, and this means there's pre-processing usually involved, that there's software that checks and fixes weather data and prepares it for use by simulation programs. Now data, if you look at the actual data at say 1 minute intervals, the solar data, for instance, this upper panel is the radiance, and there's direct normal. This is on a plane perpendicular to the beam from the sun, and the global horizontal is on a horizontal surface. And you see there's very rapid variation in this particular day. This is the 31st of August in 2008 in Colorado in the United States. That as a cloud goes by or other events, things happen extremely rapidly, much faster than an hour. Temperatures, say the dew point temperature and the dry bulb temperature, change more slowly and in much more controlled fashion. And then wind speed has a huge chatter in it. And so if you look at this and you say, okay, I'm going to make an hourly record out of this, you clearly are omitting a lot of high variation data. And that's my point. As we get into shorter time step simulations, this becomes an issue, that an hour doesn't, if its average is over an hour or some such thing, it doesn't capture these variations. The weather data items that are typically used in simulation, I've listed them here, and brief discussion of what they're used for, and some things about where you get them and what their issues are. Issues associated with those sources. So we start out with dry bulb temperature, the most obvious air temperature that's needed for exterior surface modeling, infiltration, heat gains, and ventilation heat gains, equipment performance of any air-cooled equipment. And this is universally observed, but there are local effects that if weather's observed, say, at an airport, it won't match necessarily an urban site, and we'll talk about that later. Humidity is measured either as wet bulb or dew point, or sometimes relative humidity. Those are interconvertible by software, so any one point will work. You need that for latent transfer and equipment performance, and these are commonly observed. Irradiance, which is the solar gain across the entire spectrum, and that's needed for fenestration calculations, exterior surface heat balance, solar thermal modeling. It's sparsely measured, and it's generally modeled, and we'll talk about that. Remote sensing is coming in with satellite sensing and things to help fill in the fact that this information is not measured typically. Illuminance is the portion of the solar spectrum which is visible to us, to the human eye, and that's needed for daylighting. It's rarely measured, and usually it's modeled from irradiance, which, as I said, is in turn modeled. So often it's all fabricated data in some fashion. Sky temperature is very important for long-wave radiant heat loss off the outside of buildings, and it's rarely observed except in a research context, and it's modeled using dry bulb and humidity and cloud cover. Cloud cover is used for sky models for daylighting and also for sky temperature calculation. It's generally observed, but the problem is there's many different reporting conventions, and so that's a problem, that if you're trying to use it as model input, you have to be very sure that you understand how it's being reported. Wind velocity and direction, and needed for exterior modeling and for natural ventilation. It's generally observed, but there's significant local effects that wind both direction and velocity in the urban setting will be very modified compared to, say, an airport. And also low velocity observations are typically unreliable. So let's see, ground temperature, you need this for below grade. Again, that's generally modeled. Ground surface albedo is often considered in models for irradiance or illuminance on buildings. and that's usually inferred from the presence of snow or some other assumptions about the surround. Um, Surface wetting can be sometimes inferred from rain conditions, and again, like clouds, it's often observed, but there's inconsistent reporting formats. And just a couple of examples here of how our field has to make do. Um, Values that are not important for aviation, like solar data, they don't care about the incident solar radiation, so typically it's not observed. And then aviation, if the wind velocity is low, that's fine for aviation, but we're actually interested in buildings at the distribution of wind in the very low range. That may be crucial for natural ventilation, yet that data is typically not the anemometers just don't measure it well at low speeds. So we're again hampered by how the data is observed. So you put this all together and you make files out of it with a whole bunch of columns with each of these values and then time. And this is just an example. And these days, a lot of weather files are comma separated, so they're spreadsheet friendly and you can just look at them. In the old days, they were binary and you needed special software to look at it. But there are a lot of different formats used, but as I say, many of them are directly accessible these days. A very important aspect of weather data for building simulation is so-called typical weather years. And the idea is to be able to generate an estimate of performance with a simulation of a single year. And early on, there's a scheme called test reference years that picked months from years, and it didn't actually work very well. This is a US effort. There's still some formats in the world that are called test reference years, and it's got to be sure that and that are better now, but you have to just be aware of what TRY you're talking about. The current dominant technology is so-called typical meteorological years, and to make those, say you got 15 years of data, that means you have 15 Januaries, 15 Februaries, 15 Marches. And what's done is the most representative of each of those months is selected, maybe from different years, and then they're all combined into a single year, and that's your typical year. To assess the representativeness, cumulative distribution functions are used. And this is an example. This is for solar data, but it's done for either weighted combinations of data or other measures as well as global horizontal. But essentially, the solid line here is the long-term cumulative distribution, so that the radiation level per day is across the x-axis, and the fraction of days that are below this amount are it's up the y-axis. So everything's less than what, 8 kilowatts per square meter, but you know, only 5% or below 4. So this line is the overall distribution, and then you can plot individual years, and you see some of them don't match at all, and some of them match well. And so this is used in a statistical way to pick the representative month and then combine it into years, into a full year. So there's an ongoing debate about whether TMY results are in fact typical. Here's a study that Drew actually did where he ran the actual years for a building. I don't actually know what the building is right this moment, but anyway, and then these last 3 columns are the TMY2, TMY3, and TMY4, which are 3 different US typical meteorological year publications that have come out over the last, 20 years or so. And you see that you can't really see the different end uses too well, but you know, the total here is in the ballpark. Generally speaking, you can do pretty well with TMYs for like alternative design alternatives during design development, design studies, compliance runs for codes and rating systems do well. But the problem with TMYs is there's no, except for the statistical distribution function, the cumulative distribution function, there's no real effort to represent extreme conditions. And so you can't really get design conditions. Sometimes the years are somewhat mild. And so you got to be careful using TMYs for anything that involves uncertainty, resilience studies, for instance, how is the building going to work under a really bad year? Equipment sizing is often dicey with TMYs. Net zero analysis, again, what's going to happen in extreme years of one sort or another. You can't just blindly use TMYs. And because of that, there's various efforts over the years to generate XMYs, which would be extreme weather years. And as we become more concerned about buildings that operate in a very low energy fashion, I think these years may become more widespread for using as sort of test cases for bad conditions. Now, very important thing that I've alluded to so far is, I mean, in before here is model data, and this is particularly important for solar data. The typical method is that so basically you have a weather file that has weather data on it, but there's no solar. They didn't observe it. So what's done is they use an atmospheric model that generates the clear sky global horizontal. So this is by just modeling the physics of air and taking into account elevation and aerosols and other physical factors. A clear sky solar value can be derived, and then empirical modifiers are applied that are based on the clouds that are on the weather file. And this is fine, except that, as I mentioned, cloud observations are inconsistent, and the reporting schemes have evolved over the years. The new automated reporting systems don't really do the same thing that a human observer does, so you don't have the same primary data. And this is being ameliorated by satellite observations, which are getting better and better for on very small grids over the Earth's surface. Satellite data is available that will characterize the clouds. So this is somewhat improving. Now, model data is not great. And so these plots show daily global solar radiation. The x-axis is from the world radiation. I've forgotten the exact title of this. There's a database of observed solar data that's available, and so these are observations, and these are the modeled values for the same locations for days. And again, this is two different sites. I've forgotten to note which they are, but you see that there's a lot of scatter. It's more or less one-to-one, but there's pretty big scatter. And so basically the accuracy of these models is the monthly data is pretty good on a monthly average basis. Daily data, which is what's shown in these plots, is so-so, and hourly is not good. And so the lesson here is that if you want to do glare analysis of changing lighting levels on a short-term basis using modeled solar or luminance data, you better watch your step. It's this is good enough, and in fact the best you can do for many situations for using energy, estimating energy consumption, but over a short-term basis, it's not there's a lot of uncertainty in the individual values. Models are used for a lot of other stuff. As I mentioned, luminance and sky temperature are often modeled. Then another thing is gap filling. If there's missing data, we noted that files have to be clean, so models of one sort or another are used for gap filling, often as simple as interpolation, but in other cases, actual model data. To generate short time step data, you might introduce a stochastic model of some sort or something. Synthetic sequences are sometimes generated for design purposes. Various models are used for site to site. In other words, if you've got data for here and you want it for there or for future years, and Drew's going to talk about that a little bit. Then for time shifting, if you want to account for different times that because your site is in a different place from the weather is where the weather was observed, you might shift it to the time of your actual location. So current developments in this region, in this area, are remote sensing that I've alluded to, mesoscale models, so-called. Now these are, a mesoscale model is a geographically aware model that, and these are used a lot these days for weather forecasting, that the model knows how the ground is shaped and what's going to happen to the wind, etc. And so you can potentially use that to generate better estimated data for a different location. This is being explored on a research basis, but these models are big and complicated, and they're not yet ready to run, say, on a desktop, but they may be of use. Then there's also reanalysis. All the weather data services are reprocessing old data, fixing errors, updating it, and making it better. So there are several reanalysis data sets available as well that are fed into data sets that are available for our use. So that finishes my presentation. Excuse me. So we'll move on to Drew. And I guess, do I have to do this, or Rajan, do you do it?
Oh, I'm doing it for him. So Drew, I have sent you an invite.
Okay. Can you see my screen showing now?
Yes.
Yeah, there it is. Okay, great. Okay, well, thank you, Chip. I'm going to move on to kind of a different part of the chapter. We're going to talk in this part more about climate data availability. I'm also going to talk a little bit about design conditions, which were needed for doing sizing of equipment. We'll mention some of the recent TMI data sets, and I'll mention some that are not on my list that are pretty recent, and talk about some of the issues we've seen. I'll talk about getting actual and near real-time weather data. Talk a bit about selecting the right weather data file, because even today, as we've got thousands of weather files available, there's still places where you can't get one, so how do you go about that? And then finally, talk a little bit about modifying weather files for urban heat island and climate change, and sort of showing you some of that impact. And I'll mention a few of the tools that are available today for looking at and modifying weather data and moving forward with that. So let's see, next. Chip mentioned already, but most of the data we have has been available from ground stations, primarily from airports, where it's recorded for aviation purposes. And as Chip said, solar data is rarely available. It's I think in the US it's still only about 20 stations recorded, and worldwide it's I think well under 100. Good data for temperature, humidity. We have wind data, but it's wind at the airport, and wind is definitely one of those things that's going to be very different. So other data is going to be limited and incomplete. We've got more opportunities, though, appearing. Remote sensing, particularly satellite data, has been tested against ground, and it's reasonably good. We've got there tend to be some biases, and I know they're working on that. But the beauty of it is that you can get a grid, and some of the work that NASA here in the U.S. has been doing with satellite data has been trying to make all the satellite data available, hourly data, on a grid, and they're looking at reducing that from a ½ degree latitude longitude down to a ⁄4 degree, and maybe even further in the future. So we can get very specific dealing with the terrains and everything else. The master data sets used to be hand recorded and took a long time to get in, but generally you can get data from within the last few days from sources such as NOAA's NCEI, formerly the NCDC. They support that data, collect data from around the world for the World Meteorological Organization. But design conditions and other data sets, Chip mentioned deriving the TMYs from multiple years. The design conditions, we'd have to do that as well. So we have to do some calculations and statistics to be able to put up with that. So design is what we use to size heating and cooling equipment. It's basically peak conditions out there. Usually dry bulb, wet bulb, dew point, maybe wind speed is different conditions, but there are other variables available with that. In the U.S., typical conditions are 99.6% for heating and 1% for cooling. And what that means is 99.6% of the hours in a year can be expected to be above that temperature for heating, and 1% of the hours could be for cooling. So for 1% of the hours, we're looking at 88 hours. Depending on applications, if you've got extreme wet bulb conditions or other, you may choose another percentile or even back it off, because in some respects it's how much you're willing to put up with a few modest number of hours of discomfort or potential overloading of the system. And given that most of our systems are sized with significant sizing factors, it may make sense to back off on some of those as well. I would emphasize this last point about monthly cooling percentiles. The peak month for cooling for a building may not occur in summer conditions. It may occur in a fall where you've got lower sun angles, deeper penetration of solar radiation in the space. So the monthly ones are now being recommended by the ASHRAE committee that does cooling calculations. Best source is Chapter 14 of the ASHRAE Fundamentals. There are 6,400 locations worldwide in that. The data is being wrapped up now for the 2017, and it looks like they're going to be over 8,100 locations in the new handbook, which is a big change. These are based on a period of record. Generally, at least 20 years, they're trying to expand that. In the new data set that'll be out this next spring, we'll have 1982 to 2015. I'll talk about this a little bit more, but in the ASHRAE handbook, for an earlier version of the handbook, they did some analysis to show what was happening. They had 1,200 locations that were from an earlier period of record versus a later period of record. And what they were seeing were changes in the temperature. So the annual dry bulb for cooling was increasing by 0.8 of a degree C, and the heating was coming up 1.5. That's kind of consistent with the models show for both urban heat island and potentially for climate change, but I'm not quite sure that this is all related to climate change yet. Another source of data is ASHRAE Standard 169. It essentially takes the data that's in the chapter from the ASHRAE handbook and puts in there, as well as it makes it available to standards, because it's a publicly reviewed standard and available. We're about to update it to include the 2017 data from the ASHRAE handbook as well. One thing that comes with the handbook is a station finder. It allows you to actually look at a map. You can enter a location. I've entered Atlanta, Georgia here. Each of the pin points on here are stations that where there's data for a particular location. I can click over at one location. It'll give me the WMO ID, and from that I can then go and open a file in this case, it could be a PDF, but there's also, with the ASHRAE tools, there's a spreadsheet version of this that you can download. And that's where the design conditions are summarized in a single table. The data is available, very good coverage both in North America and Europe, but you see huge sparse areas in South America, Africa, a number of countries, there's just no data. Asia, China, pretty good coverage, and it's getting better. So I'm looking forward to seeing the map for the 2017 to see how this has improved. 169, the climate data standard, also has data for, or has climate zones, and these are tied to the standards, particularly standard 90.1 is using this. So there's gives you kind of an indication of the climate. The most extreme climates being around the equator, the gray and the white in South America and Africa and on into Asia there. As far as typical meteorological data sets, Chip mentioned, you'll see at the bottom TMY3, typical meteorological year 3 data. That is kind of one of the most commonly used in the US, but you see there are data sets available throughout the world. California has its own data set now updated to include 80 locations. Canada has a set, CWEC, that has 80 locations, but I understand there's another data set coming that has 400. CIBSE, Chartered Institute of Building Services Engineers in the UK, has a set of data, and also reference years, which are similar to the TMY, as well as more extreme design years for summer conditions and future years as well. There are a couple data sets for Chinese data, an older one for Italian data, good data set for Poland, Israel. ASHRAE just updated their data set and now includes 61 locations. Iran, there's a data set from the US, has 3,000 locations, IWEC2, that does not include the US and Canada, so that's every location out. New Zealand, Australia data, Spanish data, and there's also one from UNEP, the UN Environment Program, that produced some for a number of locations throughout there. Other data sets that are out there, recent ones, the National Renewable Energy Lab has released a data set for the U.S. that is gridded data. It's different. It's derived from satellite and reanalysis, and it allows you to get much finer detail than you might with the TMY3. There have been some issues with it, but it does seem to be getting stable now. As Chip showed you earlier, we've done some testing with it, and it looks to be pretty consistent, but a little inconsistent in some ways as far as the actual data compared to the data source it was from. Recent new publications of data from Brazil, Turkey, Argentina, and a couple others that are under development right now. 3 sources I know you can get in EPW format. You can get them from the Energy Plus website. Also climate.onebuilding.org has some of these newer data sets, and white box technologies as well. That's where you can go to get the IWEC2 data set and also additional file types. If we're looking at actual and near real-time data, the actual data you need if you're going to do calibration of utility bills. You need to be able to compare the real data at the site, or at least near enough by that you can be reasonably confident that it's there, because the typical is not going to work. It's not going to match utility bills. The climate changes year to year, as you saw in CHIPS, and for that particular building, which was a small office building, it was only order plus or minus 10%. There are a lot of sources out there. The U.S. National Center for Environmental Information, formerly the National Climatic Data Center, has a lot of data. Their data is updated pretty regularly, as I said, within a day or two. Other commercial Weather Bank, Weather Source, Weather Underground, all will provide data for a fee. Some of it can be free, but a lot of it you're going to have to pay for the data available. There's also a data set that includes measured solar in Oklahoma, and I think this is probably the largest data set available that includes measured radiance for that. But the biggest issue you're going to have with any of this is how complete are they? The NCEI data does not include solar radiation. It might have missing data, so you've got to deal with gaps and filling, and Chip kind of covered some of that. So there's been some research on how best to go about doing that. But do you have the data you need? Do you have the temperature, the humidity, wind speed, and direction? Is it accurate? Or are you going to need to modify it? Or do you have cloud cover if there's no solar radiation so that you can calculate the solar radiation? So selecting the right weather file. If you're lucky, you happen to be in a large urban area or near enough by, and there's likely to be an airport, at least if you're in North America or Europe. In other locations, you may have to try to find a something that's maybe not within 100 kilometers or so, but it matches climatically what you're doing. You might have to compare the monthly statistics for some of these candidate sites or alternatives, and use some of the simulation programs to compare them to some of the climatological summaries. So you want to make sure that you're matching a long-term record, not just 1 or 2 years from there. Other opportunities, a product called MediaNorm out of Switzerland allows you to create synthetic weather. It does it from long-term statistics. Actually creates weather in a lot of different formats around there. And there are also some tools that allow you to adjust data as well. Urban heat island. Urban heat island is something that ranges in from around 1 to 5 degrees, depending on kind of the population density. It seems to peak out there. It's been measured about at that point. It's happening around the globe. We see it, you can see it happening at particular airports. Heathrow Airport outside London was pretty far out of the city, but now the city's kind of growing up around it, and the temperatures have gone, are increasing because of that. And the heat island effect essentially means that overnight temperatures, as you see in my graph here, these are 2 cases, 1 and 5 degrees change for, this happens to be Washington Dulles Airport. It tends to keep temperatures higher at night, and they stay higher till about sunrise. They do keep temperatures lower. You essentially have a lot of storage going on in the thermal mass of the city, in its streets and its roads, concrete and building exteriors, and then that's slowly released overnight. And so that effect is actually not dissimilar to what we're expecting from the climate change models as well. The impact is around the same order of magnitude that we may see from climate change, so urban heat island may compound that issue. For climate change, I talked briefly that the design conditions we're seeing have changed kind of significantly on there, reflecting warming of the climate, and I think more likely the urban heat island. The cooling dry bulb is increasing at about the same rate that the average temperature is, but that heating condition is increasing much higher. So combination of climate change, urban heat island. I would recommend you be a little cautious in using short records to look at this, or to there. it's better to have longer periods of records when you're trying to look at data and not try to look at the last 2 or 3 years, because the climate is not a constant change. It's changing all the time in different ways. It can be colder, it can be hotter, and all of that may be related to long-term patterns. But you need to capture kind of uncertainty of a larger scale, as Chip was showing in there. The 50 years shown there was probably a bit extreme, but at least 15 years to really look at that. And that's based on some research done by the ASHRAE Climate Committee. So again, if you look at the dry bulb temperature changes and cooling changes here, we are seeing more extreme in the heating and less in the cooling. So no real change in the dry bulb temperature range, although the climate change models are predicting that the diurnal temperature range may flatten a bit, so nighttime temperatures will come up more than the daytime temperatures rise. So seeing bigger increase in heating or decrease in heating degree days than we are an increase in cooling. So the climate change scenarios developed by the Intergovernmental Panel on Climate Change as part of the UN developed 4 major storylines to really describe different stories on development, economic development, as well as environmental, social, technological change, and looking at that. So these represent 4 emission scenarios. They basically derive where they think the carbon emissions would be, what the carbon level is going to be, and then re-enter that into the various models to look at it. There are kind of 4 major models being used, one from the UK, Australia, US, and others, and these are then derived, these general circulation models or global climate models, to really look at the impacts in future weather. So you've got 16 combinations, and what this looks like is these various combinations for the 4 families. You'll see the Hadley CM3 is kind of one of the highest, kind of the range. So in this case, it's showing high 2 degrees up to almost 6 degree change for the various scenarios. Some of the others are a bit lower in range, but the Hadley seems to cover some of that. So to try to bring that in there, there are 4 methods really that have been used to look at future weather. And the delta temperatures are very interesting, and the change in rainfall and cloud cover, etc. But you need to be able to redo that. There's been one process called dynamic downscaling, which uses a physics-based model really to really change that GCM result into something that can be used, modifying an existing data. Another one is an analog scenario, and I've seen that where, for example, you might take Massachusetts and say in 2050 it's going to be the equivalent of being down in New Jersey, and then in 2100 it'll be the equivalent of being down in Washington D.C. area. And that's sort of an analog looking at current climate conditions versus what's predicted here. I think that I'm not sure that that captures it. One of the other methods, time series adjustment, you basically are morphing, you're trying to change the weather pattern based on the future statistics and show how that would be by adjusting and also adjusting all the psychrometrics at the same time. There are also statistical models that are really trying to alter the frequency distribution of that, very computationally intensive, as is the dynamic downscaling. But generally you'll see a lot more of the time series adjustment or morphing out there. One example of that, the CIBSE data, the Chartered Institute of Building Services Engineers, has 14 locations in the UK. They've done reanalysis from the IPCC data and created Future climate data sets for 2020, 2050, and 2080. These represent 30-year blocks, so that 2020 is 2010 to 2040 or 2030, and then 2030 to 2070, and 2070 to 2100. They have low, medium, high cases for each of those, and there's a guide and actually weather data available. A product from the University of Southampton, also in the UK, is a spreadsheet which allows you to take a weather file, in this case an EPW, and convert it into one of the scenario more file. And it works pretty well. I've tried it several cases. The problem is they picked kind of an extreme scenario, not a range of them to capture that. But if you want to look at the variation, you can take your existing weather file and do this quickly. So if we look at TMY data, we've got the climate change scenarios give us average monthly temperature change. There's often a diurnal temperature change, a cloud cover decrease or increase, usually just a decrease, more or less solar radiation, then a change of precipitation and possibly cloud cover. So what this looks like is, if you start with this is actually from the TMY2 data. The yellow is the existing temperatures over the day, and then the four scenarios that I talked about earlier, what the temperatures would be based on that. You only see three lines because two of the scenarios actually are on top of each other. The B1 and the B2 happen to, for Los Angeles, predict the same data. There'll be a base diurnal temperature, which is the range of temperatures for that day. There'd be a scenario diurnal temperature. In this case, it was a slight decrease in the daily range. The nighttime temperatures remain a little higher and stay that way. And then there's a delta temperature in the scenario itself. So for each of them, you'll see that. Chip showed another variant of this, but I just wanted to show you, this is one attempt I did a few years ago to try to see if I could pick out from the climate statistics years that could predictably give me high and low conditions to be able to bracket this. An early attempt at doing an XMY, or an extreme meteorological year. And this only shows TMY2, but what you see there are my coolest and warmest years are not at the ends. They're the cool is closer, but the warm, and it winds up being that there's a combination of a mild year. It may be mild cool and mild warm, so that that seems to be driving it more individual than just cool or warm. So if we take the TMY2, the good news is the TMY, which these set of years covers, the TMY2, it is actually a pretty reasonable match for that. But in this case, this particular building had constant volume fans, so I'm seeing a lot of the base loads, and only the heating and cooling are changing for this. The graph that Chip showed earlier had a variable volume system. We get a lot more inter-annual variation there. If you look at what happens with climate change, here we've got three bars, a low case, a high case. These would be low and high energy years, along with the TMY. And then we also have the morph data for high and low case. The interesting thing is here in Washington Dulles, for this case, we're seeing a decrease in energy use. And what that means, for the most part, you see the red, the top bar, top end use there is the heating, and we're seeing a higher decrease in heating energy use than we are seeing an increase in cooling. And that's pretty consistent in a lot of the results. The energy use, because of fuel swapping and efficiency inherent in cooling system, is going to push much of at least the temperate zones of the world to lower energy use, but also toward electricity. For other cases, we'll be looking at, you'd be seeing different results. Source energy kind of changes it, but it's kind of about the same for what's going on there. Not a real change for Washington Dulles if we're taking into account the efficiencies inherent in the emissions related to the energy use. The cooling then becomes much more dominant in here for this particular location. Low energy building, this is a building that used about 70% less than my base case building, and you see that the difference between the high and the low years is much less pronounced, so that the impacts of climate, so as we're moving toward low and zero energy buildings, it does seem to help. The interesting thing about this is 4 different climates. We have Toronto, Los Angeles, Washington Dulles, and Singapore, very different in their response. And what you'll notice, I'll start with the lower right, you see a lot of red on the TMY heating conditions, and as you move into the other scenarios, you see a lot more of the blue that's pushing off into even the winter years or winter months for this, and the red is decreasing substantially. So that's the sort of swapping we're seeing. In the case of Singapore on the lower right, you're seeing more of a swap to increase just in heating, in cooling, because there's almost no heating there at all, except maybe for reheat in those cases. But we're just seeing just a general increase. So tropical and hotter climates, we're expecting that sort of thing. LA, which has kind of a mild marine climate, is seeing more a push away from the heating and more to the dominant of cooling year-round for that case, even in the milder months. Even in Toronto, the top left, you see a case where the heating is being pushed back, and we're seeing a more pronounced summer and even fall and autumn months as well. So lots of opportunity there. There have been a number of studies on climate change that you can find out there. The one thing I want to encourage you to do is get one or more of these tools to be able to look at the data, to be able to manipulate it. UCLA's Energy Design Tools group in the architecture department has a set of tools. One of them called Climate Consultant allows you to do psych charts like this. You can plot, bring in a weather file and be able to plot it, and also move into that, be able to look at passive scenarios that you can't quite see on the plot, but it's showing different ways that you can approach that, and that's what the lines on the side chart are showing. Elements from Big Ladder software allows you to do some adjustment of weather files and maintaining the psychrometrics at the same time. And also it's good for being able to look at and adjust weather data as well. Another program, DView from National Renewable Energy Lab, allows you to plot the data, be able to compare 2 files graphically very easily. It's also very good just if you have time series sort of data to be able to look at it. It doesn't have to just be weather data. So finally, I want to talk a little bit about the things we've covered today. For typical simulation where you're doing just design analysis or something else, and you're not pushing the boundaries of a low energy building, TMY type file is probably good enough. It covers, it's a good average middle of the road, but if you don't have a weather station, you may be able to use a climatically similar station. Or then, in worst case, you may go to some of the data synthesis analysis techniques. I'm hopeful that some of the remote sensing, the satellite data, may get us to being able to use hourly data from this, and we'll see as work progress is on that. As Chip mentioned, the sparsely measured irradiance and illuminance data really means that most of it's derived within the model, so kind of take it with a grain of salt. You need to make sure that what's there is representative of the climate and what you expect. It may be worthwhile if solar is an important part of your building energy use, or if you're doing photovoltaics or other, to do some measurements, some short-term measurements to be able to match the data and make sure that it's reasonable. I don't recommend that you stick with a TMY2 if you're doing a low energy building. Sometimes they may have specific attributes of the building that would make it difficult to be able to capture the capabilities. Urban heat island, you can have a 5-degree temperature difference between a rural and an urban situation, and it tends to keep the temperature higher at night. So it is a very different situation from most airports, which tend to be out of the city center. So you need to make sure that you're representing that and look at what's going on. There's a lot more published data, measurements of urban heat islands, and it can be a significant effect. And I know here in Washington, where I live, it can be about a 2 to 3 degrees C difference between the airports that are located out of town and the in-town measurements. Be careful if wind is important in your simulations. Wind direction, wind speed are really specific to a site, and so if you're depending on something from that remote location, that airport that's 10 kilometers away, it is likely to be very different, particularly in urban situations. If you're doing natural ventilation design, you probably need to take measurements on site, at least some short term, to be able to get a feel for what's going on and contrast it with what's recorded out there. Climate change impacts are likely to be relatively minor in the short term. We're seeing changes more related to heat island at this point for most building situations, but by mid-late century we are going to see significant changes that are going to change the fuel swapping, and you might want to consider it. But also remember that many of our buildings won't be here in 2100. They will have been retrofitted, new systems put in. Here in Washington, in the commercial corridor, all the 1960s buildings are being renovated. They literally are taking them down to the structure and whole new systems put in. So they're being designed for today's conditions, and so they will respond. So designing for 2100 may not make a lot of sense, but making sure that it's possible is good. If you're doing model calibration to utility bills, you're trying to do some measurement validation or some energy retrofits, you probably are going to need real data that match the years of your utility bills. And you should not use the typical data. So I think that's there are a lot of sources I mentioned there, and many that make it quite easy to get the data available that you want. So thank you. And at this point, I think we're ready to take questions. Rajan?
Yes, thank you very much. We have so far 5 questions, and let me try to unmute NC Balaji, who wants to ask something about reliability of machine norm file. Mr. Balaji, I have unmute you. Can you hear me? Hello.
Oh.
Yes. Please go ahead.
Hello. Hello.
Yes, we can hear you.
Yeah. How reliable is this Metron generated weather file data, sir? Because it will do triangulation or it will use models.
This is Chip Barnaby. I didn't
Yeah,
Didn't
so
hear
let me
that. Yeah,
let me repeat. How reliable is meteornorm generated weather data?
Oh, that true?
I don't have, I have some experience with it. I have talked, but I haven't really done an extensive comparison with other data sets from measured sites. The things I've seen are that it does seem to do a reasonable job if there are locations relatively close. When you start getting further away, that's where I started seeing them. I talked to one of the people at UCLA, and they were very much don't use median norm. Try to find another location first. Spend the time to do that rather than doing it using median norm by itself. I know median norm is where it has extensive data sets is pretty rigorous. I know it relies heavily on European and US data sets, but I don't know about the rest of the world.
Okay, thank you. We have another question from Shuchita Gupta, and let me see if she is still online. Shuchita, are you there?
Yes, Rajan. Hi.
Yes, please go ahead.
Yes. Hi, Drew. So this is a question for you. Basically, I would just wanted to inquire on specifically on the Indian cities. So you said we have two data sets on TMY format, one from ASHRAE and one from IBPSA. Wanted to check if there is any difference between the two in terms of the way data is sourced.
I believe that the ASHRAE data, they went directly to the Indian Meteorological Office for the data, and the IWEC were the same data, but I don't know what the conversion was, sourced through the NOAA NCEI. And that's one of the differences, but they should be similar. Periods of record are different. The ASHRAE, I believe the data are more recent than the IWEC too. And also I believe that the solar has been extensively checked by a number of the IIIT experts for the ASHRAE data set. I think it's a quite good data set.
Okay. Thank you. Yeah.
Thank you. We have a third question from Karel Kabele. Let me unmute him and let him ask a question. Karel, are you there?
Hello, Drew. Hello, Chip.
Hello.
I have one special question because I'm ahead of the task to convert the hourly data into the monthly data for simplified calculation of EPBD. Do you have some experience with some algorithm or some tool which will do that or which will help to do that? It means to create monthly data from hourly data.
You mean monthly statistics that'll be used for EPD?
Yeah.
Yeah, I can. Let's talk offline. I can help you with that. There are a number of tools that that'll do specific statistics, and if not, there are other ways we could get that data for you.
Great. Thank you.
We have one more question from Heba. Let me unmute her. Heba Ismail, can you hear me?
Yes, no problem.
Yes, please go ahead.
I'm just thanking the professors and the team, and I'm just want to ask if can we have the link of this record, this webinar?
Yes, you will be able to see this again on IBPSA website, which will take you to YouTube video. We have IBPSA University channel where you will be able to see this and also will be able to show it to your either students or colleagues. So you please check IBPSA website after 2 or 3 days earlier. Sessions are already available there.
Okay, thank you for your effort.
We have probably Last two questions we'll take. We have a Justin here. Justin, I'll unmute you and you may ask question. This is regarding TMY2 file. Let me unmute you. Just a minute. Yes, Justin, can you have us?
Hi, Chip and Drew. Thank you for the presentations. I have a question regarding building design, net zero buildings. If we are looking to get kind of a wider range of data sets than TMY simulation alone, what data sets do you recommend as an alternative?
Well,
go ahead, Chip.
doesn't the actual weather year does White Box? I think they'll make you an actual year, won't they? From the raw data.
I think so, but you can also get it from NCEI. And
right, but
the weather processors are strong enough to handle those yet now.
Yeah. So, yeah. Anyway, you could check with White Box and check with the NCEI website. So, but one lingo that we didn't mention was AWY, which is actual weather year. So the idea is to get a year that's 1997 or something or other for a location. So
those are like the ones you can download that are they basically combine to make TMY sets, but you just download the raw year set.
That's right. Right.
And for we mentioned the TMY4 from NREL. If you're working in the U.S., those actually have the AMYs available for a 15-year period up through 2014. But they don't, so that might be an easier, and they're in a format that's comma separated, so it's relatively easy to convert to whatever tool format that you're using today. They're not specifically an EPW or bin or whatever you're using.
Okay, thank you.
Thank you. And now I think this last question from Amin Moazami. Amin, can you mute yourself and ask question? I have unmute you.
Hello. Yes. Thank you for the presentation. I just have one question regarding Charles was mentioning the limits of the TMY file when we consider uncertainty, resiliency, and sizing of the equipments. And he mentioned something regarding the XMY files. Is it possible to explain more about this XMY files and if they are available already? That would be nice. And I just wanted to mention that there is a new tools also available called Weather Shift, which is based on the latest IPCC report. Have you had any experience with that tool? Thank you.
Drew, you could add to this, but XMY, by my understanding, is just a general term for an extreme year generated by any number of different procedures, picking the hottest year, coldest year, or whatever. I don't know if anybody's offering data sets along those lines. Drew, you could probably add here. So.
Not at this point. I've been working on with a colleague on trying to figure out a process which would allow us to do that, and we haven't come to any conclusion. It does seem to be temperature is the most significant driver, but we haven't figured out what temperature statistics we could use to deal with that. We have generated some. We're looking to try to set up a process to be able to take to generate more. But some of these graphs that Chip and I showed of multiple years was an attempt to try to look and see what might do that. One of the problems we ran into with trying to do an XMY that was based on the same sort of monthly selection that the Ys used, take extreme hot months, make an entire year, you got a result where it was completely out of the range of the the period of record. So you got something that was 20% higher energy than you would ever been able to get in the last 50 years, or the same sort of on the cold side. So that's, I think it's going to look more at a single year, maybe seasonal, and we're still working on possibilities there. As your question about weather shift, yes, I have seen information on it. I haven't spent any time with it, but it does seem to kind of derive from some of that earlier work out of CIBSE that Arup had done for CIBSE, and they're making more of a product out of it. I haven't been able to get there. I will add that to our list and get this updated.
Okay. Thank you. I think this is great. We had great participation from across the world. It's almost 1 hour plus 10-15 minutes. Thank you, everyone. Thank you, Drew, and thank you, Chip. This was very, very useful and very informative, educative. Thank you very much. We'll end this session now. Thank you, everyone from IBPSA.
Thank you.
Thanks, Rajan.
Thank you.